Hello everybody and welcome back to more of the grade 10 Cayley paper from the year 2001. We're on the second to last question in part C and also for the whole contest, because part C is the last part. We're on question number 24. Alright, question 24. A palindrome is a positive integer whose digits are the same when read forwards or backwards. For example, 282 is a 4-digit palindrome, and 2,882, and 49,194 is a 5-digit palindrome. 2882, 49194. Okay? There are pairs of 4-digit palindromes whose sum is a 5-digit palindrome. One such pair is 2882 and 9339. How many such pairs are there? Okay. Well, what do 2882 and 9339 add up to? Let's just explore that for a moment. So we get an 11, a 1, we also get an 11 here. 2, 1, so we get another 11, and that gives us a 12. And we got another 12, and that is the same forwards as it is backwards, so that is a palindrome. So, gold star. They gave us correct information. Alright. So, when I deal with a question that involves palindromes, and palindromes come up from time to time, the best way to write down a palindrome is by writing out an expression in terms of its digits. Okay? So what I mean by that is, if I take any old number, 348, I can write it just in terms of this 3, 4, and 8, specifically referencing that this is in the hundreds place by saying it's 3 times 100, and 4 is in the tens place, so it's 4 times 10, plus 8 times 1, although we usually don't write 8 times 1. But now I've written it out, and it's very clear which place each of my digits is in. Okay? Now, typically, for a 4-digit palindrome, we will have something like ABBA. And so A represents the same digit, and B represents the same digit. And so you can see it's a palindrome, because I can read it forward, A, B, B, A, or I can read it backwards, A, B, B, A. That's what a 4-digit palindrome looks like, but I can write it out like this. It's B times 10 plus A times 1. Okay? And actually I can group the A's together, although I don't know whether or not that's going to be particularly helpful. And I can group the B's together. It's going to be with 110 here. So now, based on a choice of A and B, I plug it into this formula and I automatically get out a palindrome, a 4-digit palindrome. One thing that we do need to note is B is between 0 and 9 because it has to be a single digit, but A is the leading digit. And if we want to ensure that it's a 4-digit palindrome, we have to make sure we don't have a leading 0. We have to start with a 1 or a 2 or something, because there's no such thing as 0,330. That's not a 4-digit palindrome, that's just 330. So that's what a regular 4-digit palindrome is, and in our question we have pairs of them. So we'll also probably want another 4-digit palindrome. So we'll write it out this way, and then we'll group our terms together, because I don't know which one we're going to need right now. Maybe not either, but usually when it comes to palindrome, to a palindrome type question, you're going to have to list out the digits in this way. That's C times 101 plus D times 110. And once again, we have to make sure we don't have a leading 0. Okay. And we also want it to add up to a 5-digit palindrome. So what does a 5-digit palindrome look like? Well, we're up to E. So it's got to start and end with the same digit. And then we're going to have F, that's the second digit, but it's also going to be the fourth digit. And then we have a single middle digit G. And we can write this out the same way. It'll be E times 10,000 plus F times 1,000 plus G times 100 plus F times 10 plus E times 1. And what the heck, we'll group this together as well. So 10,001, 1,010 plus G times 100. Okay. So this is what we've got, and we have a nice example here with 2, A is 2, B is 8, C is 9, D is 3, E is 1, and F and G are both 2. Okay. So that's a nice example that they gave us for free. So we want A, B, B, A plus C, D, D, C to be equal to E, F, G, F, E. Now, obviously, there's currently a lot of choices for A, B, C, D, E, F, and G, but only some of those choices of digits will make this equation work out. Also, E is a leading digit, and F and G are just any digits we want. Okay. Now, being 4-digit palindromes, they have similar forms, specifically these second forms, so I could actually write these together as A plus C times 1001 and B plus D times 110, and that's going to be equal to EF, GF, E. Okay? Now, one thing that you might notice, either because you've done enough math that you recognize things like the factors of 1001. 1001 is actually a pretty special number. I believe it has factors of 11, 13, and 7. I'll just double check that on a calculator to make sure I'm not saying anything silly. Yeah, I was right. But, or you could notice here, in the example they gave us, we've got a lot of 11s going on. 2 plus 9 is 11, 8 plus 3 is 11, 8 plus 3 is 11, 2 plus 9 is 11. But 11s seem to be popping up, and that makes sense. 2-digit palindromes have to be multiples of 11, because they have to look like AA, which is just A times 11. So it makes sense that there would be some 11s lurking around here. I don't know if they'll help, but I think based on this expression, we can write 11 A plus C times 91 plus B plus D times 10 is equal to EF, GF, E. So one thing that tells me is that my palindrome at the end here, EF, GF, E, my 5-digit palindrome, has to be a multiple of 11. I'm just going to double check that 12221 is divisible by 11. It absolutely is. And when you divide it by 11, you get 1111. So there's a lot of 1s going around in this question so far. Okay. So, what can we do with that information? Is that information even relevant? So it's a multiple of 11. Can we really use that? Well, right now I'm not seeing a way to use it. Okay, so my current thought process is this. I have a lot of candidates for A's, B's, C's, D's, E's, F's, and G's. Lots of digits that we can run with. What I want to do is narrow down the possibilities, because if we check the answers, the total possible pairs of palindromes that we're given are things like, I think one of them's 28, and one of them's 40 or something like that. These are small numbers. But for 9 choices of A and 10 choices of B and 9 choices of C and 10 choices of D and 9 choices of E and 10 choices for F and G, that's a lot of possible septuples of A, B, C, D, E, F, G. So what I'd like to do is narrow this down. And I was thinking maybe I could use the fact that my 5-digit palindrome has to be divisible by 11 to help here. But I'm now thinking I already sort of have some limits on what A can be and what C can be, because I mean they have to be leading ones. And I also have some limits on what B plus D can be. So if we go back to this equation, I think we can notice that A plus C has got to be at most 18, and B plus D has got to be at most 18. Right? At best, all these numbers are 9s. And I think because we're going from 4 digits, adding 2 4 digits to a 5-digit, that's not something that happens a whole lot. You have to sort of have really big 4-digit numbers and really low 5-digit numbers for that to all work out. I think we might be able to limit our choices of what E or maybe E and F can be. So our 5-digit palindrome is 11 times A plus C, 91, plus B plus D times 10, but that's going to be less than if we put 18 in that place, plus if we put 18 in place of B plus D. And that's going to be 11 times 18, we can take out the factor of 18 there, 91 plus 10. So that's going to be 11 times 18 times 101. We probably could have done this without even taking out the 11, so maybe that's a bit of a red herring. And we just grab our calculator out. This is going to be equal to 1998. So while it doesn't really limit what F can be, because we got this 9 here, so F still has free range for the most part, it does limit what E can be, because we know our 5-digit palindrome is less than 20,000. So that means E must be less than 2. And that means because E has to be a leading digit, it can't be 0, it's got to be 1. So now we're looking at ABBA plus CDDC is equal to 1FGF1. Okay? And that tracks with what we've already seen. In our example that they gave us, we had 1s at the start and the end. It turns out that was the only thing that we could have. So we were able to use those inequalities to sort of limit what E can be. I wonder if we could use similar inequalities to limit what A and C can be, now that we know what E is, and sort of play ping pong back and forth. Limit our A's and C's, and then limit our F, and then limit our B's and D's, and then finally arrive at a G. Well, let's see what else we can do here. Oh, okay. So because we have that leading 1, that forces us to get a terminal 1. So our 1's digit is 1, and then we do it vertically again. A plus C must end in 1. But A and C are both between 1 and 9. So a plus c is between 2 and 18, because at least they're at the worst they're both 1s, so 1 plus 1 is 2, and at best they're both 9s, which is 18. We already talked about that. So the only sum that ends in a 1 here is a plus c is equal to 11. So we have, in a sense, limited what a and c can be. So that's pretty good. And we remember E, F, G, F, E, which is now just 1F, GF1, is equal to, we had that 11, and then we had A plus C, 91, B plus D, times 10. Well, now we know what A plus C is. We get another 11. So we can expand this out. 121 times 91 is 11,011. Plus, and then I guess we'll bring this 11 and the 10 back together. Okay. So A plus C is 11 has actually helped us out a little bit, which is really nice. And in particular, it makes sense that based on what we've already seen, because we saw 2882 and 9339 were the palindrome that they gave us, or was the pair that they gave us, and our first digits add up to 11, just as we'd expect. And in the specific example they gave us, the middle digits also add up to 11. I wonder if we'll show that B plus D has to be 11 as well, for some reason. Okay. So we figured out some sort of relationship between A and C. So, but first we got E. E had to be 1. Now we have sort of a limiting thing on what A and C can be. So let's see if we can maybe get a handle on F, and then go back to B, D, and then finally arrive at G. That seems to be where this is going. Okay, so this is actually 1001 plus 1010 plus 110 B plus D. And this is actually 1001 plus F times 1010 plus G times 100. So we can cancel out some of this, and we can actually bring the 1010 to the other side, and we can say F minus 1 times 1010 plus G times 100 is equal to 110 B plus D. I don't know if this will help us at the moment. Okay, here. So I know F is at most 9, and so F minus 1 is at most 8, and at least negative 1, because F was one of those middle digits, so it could be 0. And G can be between 0 and 9. B plus D, well, B is between 0 and 9, and D is between 0 and 9. So actually, this is less than or equal to 110 times 18, which is 1980. Okay, I don't like that I put the 1010 on the other side, so we're going to do the same thing, but we're going to keep it over here. F times 1010 plus G times 100. Or I guess we could write that as FG, F0 if we're just writing out digits, is 1010 plus 110 times B plus D, which is less than or equal to 1010 plus 110 times 18, which is equal to 18, so 1980, which is 2990. So f is a leading-ish term, but I mean f could be 0. Right? F could be 0. So we're sort of a little off the rails here, but f times 1010 plus g times 100, it's got to be equal to this, and actually it's got to be positive, right? It's got to be positive because it's equal to this, and this is positive. So that tells me f can't be negative. Hooray, f wasn't negative anyway. So f's got to be either 0 or 1 or 2, because if it was 3, then this would be 3 times basically 1,000, so 3,000, but we've got to be less than 3,000. And actually, based on what g is, maybe we can limit f to not even be 2. But actually, no, f could be 2, because 1, 2, 2, 2, 1 was the one example they gave us. So 0 is less than or equal to f is less than or equal to 2. Okay. Can we narrow that down anymore? I don't think so. I suppose, just going back to this page, if I had kept this extra 1010 on the other side, I could have made the argument that f minus 1 times 1010 plus g times 100 is equal to 110 times b plus d, so that's also got to be positive. So f minus 1 would have to be positive as well. But let's just do cases. Because there's only 3 things, and I don't think I'm going to, because I've already exhausted my limit on b plus d, I don't think I'm going to be able to get a better limit on what f is. Okay, so if f is 0, then that means that g times 100 is equal to 1010 plus b plus d times 110. Now, at worst, that is 110 if b and d are both 0, but at best, this is 900. So no values for g here. So this case was a bust. Now I know I can get some with f is equal to 2. How about f equal 1? Well, then I'd have 1010 plus g times 100 is equal to 1010 plus b plus d times 110. I'm suspicious that this might not work. So those 1010s cancel out. And so we're left with g times 100 is equal to b plus d times 110. Well, we can divide by 10 on both sides. So g times 10 is equal to b plus d times 11. So g times 10 is equal to 0 1, 2, 0, 10, 20, 30, 40, 50, 60, 70, 80, 90. And b plus d times 11. Well, that can go all the way from 0 up to 11 times 18. So that could be 0, or 11, or 22, or 33, 44, 55. Most of these aren't working. 77, 88, 99. I don't need to do any more because the next one's going to be 110, but G could at most be a 2-digit number. So we're definitely not going to have an equality. And so the only one that seems to work is these zeros here. So what if we had G is equal to 0 and B plus D is equal to 0? So that last one means that B is equal to D is equal to 0. Okay. So this should give us some cases. So what do we know? We know E has got to be equal to 1, and in this case, F is 1. So our 3-digit polynomial is 11011. And we know A plus C is equal to 11. Now, are we asked for ordered pairs or just regular pairs? There are pairs, one such pair, how many such pairs? So it looks like 28823 or 9339 is the same pair as 9339 2882. So we'll do our counting. If we've made a mistake and we do want ordered pairs, even though it's not stated in the question, in which point I will cry bad question design, if it should be apparent in our answers because we'll get half the answers we want. So they don't say in the question that 2882 and 9339 is a different pair than 9339 2882. So we'll assume that we only count that once. And we'll know we're wrong if we start getting answers of, well, there's a total of 14 or 20 of them. Because we'll know we're off by about 2. Because each pair would give you 2 ordered pairs. So back to the question. So we'll make the assumption then that A is less than C. We'd say less than or equal, but because A plus C is 11, where it's only going to we'll only need the less than sign. So we could have A is 1, but then that would be C is 10, so that's not going to work. 2 and 9, 3 and 8, 4 and 7, and 5 and 6. So that's 4 pairs of leading numbers, and everything else is worked out for us. So 4 pairs, and if we needed it, 8 ordered pairs, because you could always swap what A and C are. I don't think we'll need that, but we might have to come back to it. Because 4 is a surprisingly low number, we might need 8 to start getting and seeing some of the things like the 36 and the 40 and the 44 that we have in our possible answers. Okay. So that was F equals 1, and we got 4 cases out of it. Now our last case, F equals 2, I hope we get, at least 30 or something out of this. So if F is equal to 2, then we have 2020 plus G times 100 is 1010 plus 111 B plus D. So those guys will cancel out, and we will be left with 1010 plus G times 10 is equal to 110, or sorry, not G times 10, G times 100, 110 B plus D. I'm going to divide by 10 again. So we'll be left with 101 plus G times 10 is equal to 11 B plus D, and so we're going to get the same sort of lists we had last time. 101 plus G times 10. G is at least 0, so this is at worst 101. 111. 1, 2, 1, or 1, 2, 1. Now 1, 2, 1, that's 11 squared, so I think that should definitely work. 161, 171, 181, and 191, and that's it for our list of 101 plus g times 10. So now how about 11 b plus d? Again, we only need to go up so far. So 0, 11, 22. We really don't need any of these, so I'm going to skip ahead. 99, 110, 121, 132. I need to go all the way up to 198. So that's 143, 154, 165, 176, and 187. So the only one that matches, again, so hopefully we're not in for another only 4 answers, because otherwise I don't know what we're going to do, is 121. And that forces G to be 2. So our palindrome, our 5-digit palindrome, is the one that we saw at the very start of the question. 1, 2, 2, 2, 1. And we know that B plus D has to be equal to 11 as well. Okay. And we know E is equal to 1, F is equal to 2, and we also know that A plus C is equal to 11. And once again, we're going to say A is less than C. So we get 2, 9, 3, 8, 4, 7, and 5, 6 as our possibilities. And now B plus D. We get that B is 0, D is 11, that doesn't work. 110, that doesn't work. 2, 9, 3, 8, 4, 7, 5, 6, 6, 5. Now I can complete this list even if we are doing ordered pairs, because once we've picked a leading one, the AC already determines which of our pair is going to be the lowest one. So it already determines which one is the first one in the ordered pair. So B and D can really be anything. So we'll just complete this list. And can't be 10 anyway. Okay. So we have 1, 2, 3, 4, 5, 6, 7, 8 pairs. So in total we need 4 times 8, because we could we take any pair over here like 2 and 9, and any pair over here like 8 and 3, and we get 2, 8, 8, 2, and 9, 3, 3, 9. And that's different if so doing this pair and this pair are different than doing this pair and this pair. All right, one of them gives us 2, 8, 8, 2, 9, 3, 3, 9, and the other one gives us 2, 3, 3, 2, 9, 8, 8, 9. Both of them will work. Both of them will add up to 12,221, but they are distinct. So that's just an illustration of why B plus D gets a more complete list. But we can pick any pair for AC and any pair for BD, and when we have independent choices, we multiply the possibilities to get the total number. If you don't believe me, by all means, write out them all. You're going to get 32 pairs of palindromes. And we already worked out 4 pairs in the F equals 1 case. None of them will overlap because they add up to a different 5-digit palindrome sum. So we are done the question. So there are 4 pairs that add up to 11,011, and 32 that add to 12, 221. So 36 pairs, and we didn't need to do ordered pairs, so it all worked out. 36 pairs, I think that was the middle answer. Yes, it was. So C36, and that does it for question number 24. So we have one more question to do, and we're going to do that, question number 25, in the next video to wrap up the 2001 Cayley. Thank you guys for watching, and I'll see you in the next video.